Hi everybody, and welcome to part 4 notes. This will be our last set of notes for our unit, and we're going to continue talking about equilibrium today, and we're going to discuss what is known as Le Chatelier's principle. All right. And what this really is going to talk about is when a reaction is at equilibrium, what's going to happen if we mess with it, if we change something. So Le Chatelier's principle, when a system at equilibrium is stressed, and by stressed we mean we've changed something, the system, meaning the reaction itself, shifts in a direction that partially relieves the stress. All right. In other words, the reaction is going to respond by trying to undo the stress. So let's go through and talk about the different types of stresses or changes that could be made to a reaction at equilibrium. So the reaction we're going to look at today is the Haber process, all right, and that is the synthesis of ammonia from atmospheric nitrogen, N2, and hydrogen gas. So here is our reaction. It is an equilibrium reaction, so you see the arrow going in both directions. Our first change or stress that we could do is by changing the concentrations of one of my components of the reaction. So let's go through this example. Our stress is that we have added more nitrogen. All right, so that's the stress. I think the simplest way to go about this is just to say to yourself, okay, what was the stress? What was the change? What's the opposite of that? All right, because that's going to be the reaction's response. And how does that happen? So the stress is that you've increased N2. All right, that was your stress. Well, what is the response of the reaction going to be? Well, it's going to be the opposite. It's going to be to try and take this away. Well, how do I take it away? How do I use up N2? So you need to use up, well, to use up N2, I want more of the forward reaction because that forward reaction is going to use up N2 and force it to become NH3. All right, so the stress was adding more nitrogen. The response is always going to be the opposite of that stress. It's going to be to take it away. How do we do that? All right, we shift right. The reaction will shift to the right. Now, because that's happening, other things, you've changed one thing, everything's going to change. If the reaction is going to shift to the right, well, that means I'm going to make more ammonia, right? And I am going to end up using up some of that hydrogen. All right. So by adding that nitrogen, that was my stress. Well, the reaction's going to try and take it away, which means it's going to shift right, producing more ammonia and using up that hydrogen. All right. Okay, so let's continue. It's okay if this is a little unclear at first. The more practice you do, the better you're going to get. What would happen to the concentrations of nitrogen and ammonia when hydrogen was taken out of the system at equilibrium? All right, so what is your stress? All right, so the stress is that hydrogen was taken out, so that's H2 was taken out. So what is your response going to be? You're going to try and make more hydrogen. Well, how is that going to happen? You're going to shift to make more hydrogen. You want this reaction to go in the reverse. So we say that that is shifting left. We also could say that the reverse reaction would be favored. Either way is fine. All right. Well, if I'm shifting to the left, what's going to end up happening? I'm going to increase N2 and NH3 is going to go down. So what will happen to the concentrations of nitrogen goes up and ammonia because hydrogen was taken out of the system. So really always go through the process. Say, what is the stress? The stress was taking hydrogen away. The reaction is going to respond by doing the opposite, making more hydrogen. To make more hydrogen, we need the reverse reaction or a shift left. If we shift left, we're going to make more N2 and use up that NH3. Okay. How would an increase in ammonia affect the concentrations when equilibrium is reestablished. So let's just rewrite the reaction because I didn't write it again here. All right, and that's going to be NH3. None of that's changing. So what is my stress? My stress for this question is that I've increased NH3. All right, well, if I increase NH3, what's the response going to be? It's going to be to try and take it away. It's going to be to take it away. How do I take it away? I shift to the left. All right, and that is going to increase my N2 and increase my H2. All right, so that's kind of how you play with these as you go. Now, all of these stresses we've been talking about have simply been changing the concentrations, increasing the amounts of either your reactants or your products. Another stress we can do is we can change the temperature. And by changing the temperature, we're manipulating the energy involved in the reaction. So for this, I have to tell you whether a reaction is endothermic or exothermic, and I can do that in a couple of ways. I can write it like this. So here is my Haber process again, and I can write energy here as a product, okay? I could also tell you that it is an exothermic reaction, or I could say that the delta H is negative. I could do any of these three, and that gives you information as to what's going on with this reaction. When it is exothermic, we think of energy as a product. If it was endothermic, we would think of it as a reactant. Once it's thought of as either a product or a reactant, just treat it like you would treat the concentrations of anything, okay? So what will happen to the reaction if energy is added? So your stress is that you added energy, right? The response is going to be the opposite of that. So you want to take energy away or use up energy, if you like thinking of it that way. All right, so if I need to use up that energy, that means I need to shift left. So I'm going to shift to the left. All right, that's the big one. It's going to shift left. Well, if I shift left, then the concentration of N2 and the concentration of H2, they're going to go up because I'm going to have that reverse reaction going on. The concentration of NH3 is going to go down. Okay, so you can see where we can get a whole bunch of different questions going on just by giving you a balanced equation at equilibrium and telling you about the energy. All right, our last change of condition that we're going to talk about is for changes in pressure. Now, changes in pressure are only going to impact the concentrations of gases. All right, so if you change the pressure, that actually changes the concentration of any gas. An increase in pressure will shift the reaction to the side that has fewer moles of gas. All right, so fewer moles of gas. If you end up looking at a balanced equation and they have the same number, an equal number of moles of gas, then changing the pressure will have no impact. All right, so what does that look like? Again, let's look at our Haber process here. So just rewriting it again. All right, these are all gases. All right, all gases, and I'd make sure to make that clear. They're all gases at room temperature. Okay, so what do I mean by fewer moles? Well, you just simply add up the coefficients. All right, so here on the left side of my reaction, I have 1 mole of nitrogen because the assumed coefficient of 1. I have 3 moles of hydrogen, so I have 4 total moles there. On the product side, I just have 2 moles. Okay, so if I were to increase the pressure on this system, the reaction would shift to the right. All right, so final question. What conditions will maximize the formation of ammonia in the Haber process? All right, so here's our, again, balanced reaction. Remember, this is exothermic, so I should have plus energy here, but I'm writing that in for you now. All right, so I want to maximize the formation of ammonia. I want this reaction to be shifting to the right as much as possible. So if I want to maximize that formation of ammonia, I want it to shift right because I want the forward reaction to happen. Well, what can I do to have it shift to the right? Well, first let's look at concentration. All right, remember the reaction's going to respond by trying to undo whatever stress you put on. So if I increase nitrogen, if I increase the concentration of N2, the reaction is going to respond by trying to get rid of it. Well, if I get rid of it, that's the forward reaction. That's what I want. I want that forward reaction to happen. Okay. All right. So I'm going to increase that N2. It's going to shift it forward. I'm going to do the same thing for hydrogen, because if I stress it by increasing that hydrogen, the reaction is going to respond by trying to take that hydrogen away, and then it's going to do that by shifting right. Well, what do I want to do with this ammonia? I want to take that ammonia away. So as soon as I make that ammonia, I want to get rid of it, because if I take it away, the reaction equilibrium is going to shift to make more. So I want to decrease the concentration of ammonia. So that's what I want to do with all of my 3 concentrations. Now, what about pressure? And we just talked about this up here. Remember, on my reactant side, I have 4 total moles of gas. On my product side, I have 2. A reaction is going to shift to the side with the fewer moles of gas if I increase the pressure. So I want to increase my pressure. So it will shift to the side with the fewer moles, because the side with the fewer moles is what I want to maximize that ammonia production. Finally, temperature. Okay, well, for temperature, this is an exothermic reaction. We want to make as much ammonia as possible. Well, energy is a product. So if I take that product away, the reaction is going to shift to try and make more. We want more ammonia. So we want to lower the temperature. Okay, so we want to take that energy away. We want to lower that temperature, but we need to be careful. Okay, so be careful with the temperature. Why do we need to be careful? Well, because we need to make sure that this reaction still takes place. So you need to make sure that the temperature is still high enough to reach that activation energy. So you still need to reach that activation energy. All right. Okay, so we're going to do a bunch of practice on this in class. I hope you have enjoyed our unit on reaction rates and chemical equilibrium. Have a great day.